Traditionally, combustion is used for power generation, propulsion and heating. However, our research has shown the potential of combustion to produce carbon nanotube. Very interesting.
Multi-wall carbon nanotubes is a nanomaterial with tubular structure consists of multi-layer walls made of carbon. It is 1,000 times thinner than our hair, but it has remarkable properties. Since carbon nanotubes is 100 times stronger than steel and up to 100 times more conductive than copper, it is used as additive to the base material to improve the end product performance. However, multi-wall carbon nanotubes is relatively expensive material, and this fact become a major hindrance of carbon nanotubes application in various products in the market such as battery, solar panels, composites, sensors, and semiconductors. Thus, it is our main goal to reduce the cost of carbon nanotubes with highly efficient synthesis process offered by novel flame technology to make carbon nanotubes more accessible for various consumer-based applications. This is why we introduced a novel application of flame technique in the synthesis process of multi-wall carbon nanotubes. Flame synthesis has significant advantages in reducing production costs through minimizing external heating application of furnace. The flame will provide both heat and carbon source for the synthesis process to occur. Furthermore, flame synthesis also is proven capable to enhance production rate of CNT with higher synthesis rate through natural decomposition of hydrocarbon. Thus, application of flame synthesis not only reducing the total production cost of CNT, but also helps to reduce carbon footprint in the production of CNT by minimizing utilization of electricity. The synthesis process utilizes a methane flat premix flame as source of carbon and heat. A flat flame provides one-dimensional variation of temperature which ensure uniform and maximum carbon nanotube growth region. Flat flame is also ideal for development of theoretical model for the flame condition and the synthesis process. To establish a flat premix flame, the burner outlet is fitted with a sintered stainless steel metal. Radially uniform growth temperature produced by the flat flame enable a temperature control synthesis process. The growth temperature decreases linearly as the growth region moves away from the flame.
Having expertise in combustion science and modeling, we managed to understand the synthesis control within the challenging environment of the flame quite well. The model that we developed let us understand where to grow carbon nanotube within the flame. And the lab-scale synthesis system that we have now may produce dense nanotubes within minutes. The detailed characterization of the nanotubes shows we get what we want: a crystalline structure, multi-wall carbon nanotube with average diameter of 30 nanometer. With 6 ISI publications, 3 Scopus publications, and 40 citations since 2017, we successfully filed a patent last year related to the water-assisted synthesis.
Malaysia currently producing around 100 million metric ton palm oil waste every year that has potential to be converted to biogas. Utilization of biogas from palm oil helps to turn waste into wealth in form of highly valuable nanomaterials product. There are several projects that currently producing biogas in Malaysia. The biogas producers can be utilized for various applications such as an electricity production, power generation, or even vehicular utilization. Utilization of biogas as carbon source for CNT synthesis could further enhance utilization of biogas produced using palm oil waste. This will eventually beneficial not only to the farmers, but also our country through enhancement of agriculture industry. Fluorescent 3 synthesis system utilize a flame synthesis process which is a highly rapid process, a magnitude faster than conventional CVD synthesis process with flexible throughput. CNT can be produced in various ways. Conventionally, CNT is produced using arc discharge, chemical vapor deposition, and laser ablation method. This method may produce different quality of CNT with varied cost of production. Flame synthesis, however, is considered as an alternative to the CNT synthesis method. It, however, capable of producing similar CNT as per conventional method, but with much higher growth rate, throughput, and efficiency. Besides low production cost,
The quality of our product also increases with the introduction of flat flame technique in our latest synthesis system. Higher level of temperature control enable us to produce bespoke nanomaterials with specialized properties for niche application. Currently, our synthesis system fulfills the requirement of TRL4 with the integration of the synthesis process control system to a centralized control system.
The test rig used to develop the synthesis process was designed and fabricated in high-ref laboratory. The synthesis process utilized premix flat flame with mixture of methane and oxygen gas. The catalyst is nickel nitrate vapor with nitrogen as carrier gas. The overall synthesis process is designed to be relatively simple. Place a ceramic bit at a certain height above burner before coated with catalyst vapor. Once ready, the coated ceramic bits are exposed to a flat flame for a certain period of time and the CNT are collected within minutes.
The synthesis system utilized ceramic bits coated with catalyst as nanomaterial growth site. The bits turn black, filled with nanomaterials when exposed in flat flame. The synthesis chamber is filled with the coated ceramic bits, which form a fluidized bed that freely move to allow for continuous growth of nanomaterials. Once the nanomaterial reaches certain length, it will detach from the beads and collected, and inception and growth of new nanomaterials will commence, creating a continuous production process. Analysis of the synthesized CNT using fluorescein-3 shows that the CNT producers has very consistent morphology and characteristics. Furthermore, with high level of control over temperature within the synthesis chamber using the flat flame, fluorescein-3 also capable of producing CNT with varied properties such as diameter and crystallinity. The diameter of the synthesized CNT using fluorescein-3 process is very uniform with average diameter of 30 nanometer, which is comparable to the one available in the market.
Market analysis shows that there are 20 research organizations that we know quite well within and outside the country. They are our main target market considering the research collaboration that we have with them. Local industry research and development and manufacturers are those that we need to reach out via extensive marketing.
Market trend of carbon-based nanomaterial is very promising. Since our target customer is from Malaysia, the trend that shows highest market share in the Asia Pacific region in 2023 is very good news. The commercialization landscape of nanomaterial produced by the system spans various applications from mechanical, electronics, and multifunctional application, most of which are at the early stage of commercialization. Our CNT product, which add comparable diameter to other CNT in the market, ensure its competitiveness to entice new customers. We are quite confident to penetrate the market since, to the best of our knowledge, there is no large-scale producer of CNT in the country. The supplier who are not the nanomaterial producers sells in small volume. So by positioning ourselves as local producer who can sell directly to academia market segment and scale the production to sell in large volume, we are quite competitive. By convincing the industry players to switch to CNT as the additive in their product, we may get a new market share that will be first in the country. We hope to place ourselves as manufacturers of low-cost CNT and supplier who has large share in the market. So far, the local suppliers like NE Scientifics and BT Science do the business at low volume. Large share is mostly dominated by overseas suppliers, though most of them are vendors and not producers. Currently, we have letter of intent from several companies including Mimos, Anjong Technology, and AT. These companies provide guidance for commercialization process of our product, development of our synthesis system, and collaboration to produce suitable biogas for our system. Besides that, companies such as SureTreat have shown interest in our CNT to be used as an additive to improve their coating products.
We are glad that since last 2 years, the project gained various awards locally and abroad. The silver medal was gained when we presented the first generation of synthesis system. As a combustion scientist, I believe that flame synthesis has a bright future. It's fast and it can lead to economical synthesis of carbon nanotube. I'm quite excited about it, and as a project leader, I believe it has a bright future for job creation, income generation, and hopefully it will spearhead the nanotech business in the country.
From metal science point of view, synthesize CNT without vacuum and furnace is very good idea. And in this research, okay, we try to focus on synthesized CNT with fully control in terms of atom arrangement, geometry, and purity.